Mm. So anyway, let's get started. I have quick revision of what we did last week about the battery and energy storage. So key thing is we now have to understand more about the rechargeable battery. In the past, rechargeable battery mainly refer to a battery that is only charge in, charge out. In the past, I think the battery can be separated into a battery able to provide like energy output. But recently, then the battery, lithium-ion battery, are commonly being referred to rechargeable battery anyway. When we talk about a battery today, we don't need to mention that battery will be rechargeable or not, because mainly for power application, we all talk about the rechargeable battery, like lithium-ion battery. So we have a so-called lithium ion, IRON, not lithium ION. So later on, we'll discuss what that kind of lithium ion battery like. And then we're also going to talk about the battery safety and also what kind of parameter will be important. So today we're going to go for a few items like the lead battery, lead cat, little metal, hydride, and lithium ion battery, and some basic parameter. And then we go for some future batteries. So I think last time we also mentioned about the lead battery. So lead battery has been developed for many years, nearly 2,000 years since 1859. So we can basically classify the lead battery by using the silver type or non-silver type. For silver type, the inside will be some gel. So in this case, we don't need to worry about how to add on or improve the electrolyte inside. The another one is for valve regulated. There will be some electrolyte and regulate the density. In case the electrolyte water become evaporate, you can add on some new liquid there. So basically, both of them has been used in EV in the old day. But of course, nowadays we do go for the lithium-ion battery. But you can see that the lead battery, the lifetime is not that good, so-called lifespan, only 200 to 300 cycle. So that means we have difficulty to really to use them for electric vehicle. But of course, in the early stage, then we still use lead battery for the EV. And then this kind of battery still has some disposal problem because it still have lead inside. So the people, how they dispose them, and after they will pull away the sulfuric acid into some proper container to recycle them. And then the lead, they also need to be moved from the battery. So to handle this kind of use the battery for lead is not an easy job because you need to handle with a poisonous lead and also handle with sulfuric acid. But this lead battery is not that harmful as compared to nickel cadmium. The next battery I try to show you called the nickel cadmium. They are even more dangerous because cadmium is really, really dangerous material. So that's why we do prefer lead because highly mature. We know how to handle them properly. And then, however, nickel cadmium has been developed roughly about, say, 25 years ago. That would be a really good alternative as compared to lead acid. So here will be a basic structure. You can see the lead-acid, really similar to all the start battery. Today, all the start-up battery in a vehicle, in any vehicle, basically based on the lead-acid. So the two polarity on the top here, they usually cover when you deliver or when placed under the storage. You must do that because there's safety issue. The two terminal able to provide high current. In some case, if you drop some metal, maybe metal bar or spanner, then the short circuit current is so high you can able to make the spanner jump up to hit you. So for the nickel cadmium battery, so this one based on technology called the cadmium. So this battery has a much higher density as compared to the lead acid. So that's why many people prefer to switch to this battery roughly about, say, 20 years ago. But this battery still have problems called the membrane effect. So this membrane effect able to lose some membrane, lose the capability after a certain period of time. So that's to say, if a battery like this has been charged up to 30%, if you don't discharge completely and recharge again, then that 30% will lose out. So that's why this membrane effect is not that welcome. And because the ROHS requirement, ROHS, restriction of hazardous substance requirement all over Europe, so this kind of the battery gradually get retired. You see some of the electronic are still using this cadmium as a solder or some kind of the substrate. So that's why this material, including all the electronic or the battery, are gradually become retired. So here will be one of the power battery look like the CAD. You may see many of the AA size, 3A or 1A size of battery. They also in the form of cadmium. But for power battery, it will be look like this. And the nickel metal hydride has been really popular roughly 20 years ago, maybe 25 years ago. And during that time, this one come up. Firstly, they don't base on cadmium. So a little bit safe compared to cadmium battery. And the energy content can able to provide much higher as compared to nickel. You can see that 40% higher. So that's why people prefer to use this one. I think in the early stage, like some of the popular vehicle, like Prius, Toyota Prius hybrid vehicle are using this nickel metal hydride battery. So this battery, however, gradually being replaced by the lithium. So you can see that some of the battery company, like the GP battery, they tend to use this kind of the battery, but gradually they find that the manufacturing of this battery may be more expensive than the lithium. So many people now switch to the lithium battery manufacturing. So this is how it look like, or the power battery look like. The battery voltage not really high, roughly about, I think, 1.2, 1.3 volt. So lower than the normal dry cell battery. Normal dry cell battery based on the manganese and carbon technology, the voltage about 1.5. So if you use this kind of battery as an AA battery for replacement for those home use dry battery, then voltage slightly lower. So may not all the equipment able to stand for it. Sometimes the impedance is too low, and some of the equipment may find difficulty to work with this kind of the low impedance battery. So of course, lithium battery is something we like to discuss further about that. Today, all the energy storage are based on lithium, mainly because the cost is much lower. Nowadays, the lithium-ion battery is so low cost, for probably sometimes the costs are more approach similar to the lead-acid battery nowadays. So that means in the old day, when you have a lead-acid battery of a large system, in the backup system for the factory, for your building, for the hospital, the data center, they usually have a big room with a lot of the lead-acid battery. But nowadays, they all gradually switch to the lithium because much cheaper. The cost is not that much different, and also maintenance, also simple. You don't need to worry about the leakage. But having said that, lead battery is really mature technology. It's really safe. If you talk about the safety, explosion of fire, this kind of the statistic, lead battery are much lower compared to lithium. So that means for some highly safety, people still prefer to use lead because they like safety will be the high priority. And lithium-ion battery will be low maintenance. You don't need to worry about maintenance because of lead battery, every month or every 2 to 3 months, you need to recycle a little bit so that you don't lose all the energy. So, but for lithium-ion battery, then because leakage is so low, so even though put it there and touch them for 6 months, you won't lose the capability. The thing is, all the battery like that. If you discharge the battery to a certain level, lower than the low limit, the battery will die, you kill by itself. So you can't use it forever. Even though push up, recharge up, you still have that kind of the scenario. So that's why we do prefer, everybody know that lithium battery, you do need to have some kind of maintenance. Every 6 months, you need to charge it, maintain a certain level, maybe discharge it so that you can have some cycling. If you don't recycle the battery properly, then the lifetime is getting worse. So that's same for the lead acid battery as well. And for the battery, you see we got a different kind of charging rate. We call the C rate. So 1C, 2C is quite popular for this kind of lithium-ion battery anyway. So here will be the shape. I think we also discussed about that. We got cylindrical shape. The number there, 21700, responsible for the size. The first 2 digits responsible for the diameter. The next one responsible for the height. And then we also have different kind of the shape. You can see that some of them, the package will come with some parallel and series connection. If you see the package, you say 2S, 2P, that means it's 2 in series and 2 in parallel. That means totally 4. So that is one of the standard we try to use. Most of the battery package, they usually come into a number of battery cell, connect in parallel or series, like in this configuration. So the battery pack is another technology we need to look into. So including how we connect them together, how we put the fuse together, which one we can parallel. Usually in the factory, when they come out, then they will do some shorting. All the battery cells have really similar behavior, similar characteristic. You can put them in parallel. Because parallel is quite tricky. Parallel, you need to ensure that their impedance against each other will be equal, really much similar, so they don't have any circulating current. And when you want to come up with the current, they all share the current equally. So that's why they do some sorting first. And then in series connection is not that important, but still very important. Usually within a package, we'll put all the similar battery, the same kind of characteristic battery, exactly the same inside the same package. So, but parallel will be more important. So of course, inside the package, they also need to measure the voltage and also temperature, ensure they're safe. So usually, they only put one sensor, temperature sensor, because they think within the package, all the temperatures should be the same because they are closely to each other. They have a lot of metal content to ensure that they share the same kind of temperature. For the aging, lithium-ion battery, the aging usually about a few thousand cycles. That's quite common. So most of the manufacturers today, they will declare that their battery will be about 5,000 cycles or 7 years. For EV manufacturer, they usually try to say the guarantee of the battery will be within how many kilometers. So that means that kilometer will usually refer to how many cycles. For instance, one fully charged battery can run for, say, 350 miles, then they can use them to calculate about the lifetime of the battery. So probably something look like 7 years will be quite a good long, and also 5,000 cycle will be quite good long. But 5,000 cycle, as I said, is not always 5,000 cycle. 5,000 cycle only in some special condition of operation, you can have 5,000 cycle. For instance, they will test the battery at 0.2 C, with only 20% of normal current. That's a really safe current for the battery to operate. So under 0.2 C, they have 100% charge and discharge, then can able to run at 5,000 cycle. But seldom the battery able to operate at 0.2 C, usually 1 C, maybe 2 C. So that 5,000 cycle is not realistic, usually only about 1,000 cycle or 1,500. So that means if you try to charge and discharge your vehicle one cycle once a day, maybe twice a day, you can use your battery vehicle for about 1 year. So that's how they come up with that parameter. So usually the best operation point for the battery will be within 20% to 80% of the SOC. Anything within that range, we are able to prolong the battery lifetime, say up to 5,000 cycles. If you don't do that, then the lifetime will be less than you expected. So the bottom 20% and top 80%, beyond 80% is not very good. you can see that when the battery come up to charge up to 80%, just like rush over or the fill up, you want to pump more energy there. So you need to have much higher voltage to charge up. The impedance of battery will getting much higher. So you need higher energy, higher current source. So that means that will be more damaging to the battery. So that means for the after 80% or 85%, then we'll change to another mode of charging. Later on, we'll show you the charging profile, then that will save the battery. So that means if you take a car outside to charge to any charger, usually the constant current mode charging will be up to 80%. After that, you will switch to the constant voltage mode. And second mode will be much time consuming. So nobody will like that because I think the charger outside are really jammed. Many people are waiting for after you. So probably after the CC mode charging, you need to go because for the CV mode, you take another quite a few hours. Nobody will like you, especially the one queue behind you. So for the new development for battery, you can see that we have a new research going on, like lithium sulfur, lithium oxygen, lithium polymer. They are all new research development. So I checked many research papers. They can able to provide higher energy density. Something more than some 30% is quite common. Something will be double. So that's something we need to look into. And also we got the nanotechnology. Nanotechnology, they try to make the connection part, like the electrode have some nano connection. So that means they're able to provide much better contact surface. You can see that the current itself really a good contact surface. You want to increase the current density. To do this one, if a flat surface may not able to provide you good contact surface, but if they all have a lot of the nano contact, they will therefore increase the contact surface. In this case, their current capability can also be increased. So that's how they write. So that means internally, the energy content are more based on the lithium metal and also based on amount of the electrode. But so that means even though you use nanotechnology, doesn't mean your energy content can be increased by a great deal. It only help you to improve the CV, the current density. Of course, simultaneously, you may improve the current density by energy density by a certain percentage, but it won't be double, 3 times, or 4 times. So only have some improvement. But the current density can be increased by quite a good ratio. So that means nanotechnology is good, but doesn't mean you can improve the battery by a great deal, only a certain percentage. So of course, there's other lithium technology. For example, like we are looking into some polymer electrode. Polymer electrode means the electrode rather than pure metal. We try to make some new technology so electrode become more flexible. So in this case, for some battery, we don't like to have solid battery. If you want to have battery in certain corner of a vehicle, certain corner of package, you may consider some kind of a more flexible battery. So in this case, you can see that we have the polymer electrode SPE that can be including this PMMA, this kind of new material can be embedded in the electrode to help them. But you can see that this kind of the polymer-based system, their energy density may not be as so high as compared to conventional one. So from the research paper, you can see that the new battery, like the lithium sulfur, they promising have a much higher energy density. So in here, you can see that the parameter can go up to 400 Wh per kilogram. 400 Wh is more than double compared to normal lithium-ion battery. So, but the number of cycle, 2,000 cycle without any aging. So usually our battery, 5,000 cycles is a long, only in perfect condition. Usually after 500 cycle, you can see some kind of the degrading. Like your phone, if you after your phone used for 6 months or 1 year, I'm sure you can feel that the battery capability getting less. I don't think your phone can able to last for 5,000 cycles. In theory, they all advertise your battery can 5,000 cycles, but for practice only 1,500. And then you can see that 1,500. So that means your phone use after one year, probably you think that the energy content may drop by at least 10 to 20%. It's quite common. Everybody feel that. So that's even though EV as well. low EV can able to run for 5,000. It's a kind of the gimmick. I think 1,500 is more realistic. After your EV used for about 1 month, probably not 1 month, maybe 1 year, you can feel that your energy content can drop by something look like more than 10%. So this is quite a common user point of view. They can feel that. But anyway, so there's a number of important parameters for battery. Like in here, I show you a few parameters like the energy density. Now, the density have a two-way to present that. One is called energy density per unit volume, per unit liter, L. Because sometimes the size is important. You don't want an EV have a too big battery there. And that will be the weight. Vehicle is really scared about the weight in kilograms. So that means WH per kilogram is another parameter we need to look into. Of course, another way would be the power. Even though per unit kilogram, how much power our output. Of course, we like a battery have a high current, high power. So another way would be the power. So there's a number of parameters we need to look into, like the C rate and also the number of cycle. So now let's look at this basic parameter. I think you all know that. So if a battery 100 Ah, so Ah is mean the energy really related to energy content. They usually don't mention about the voltage. And why is that? Because they assume that the battery voltage will be more stable and change. So they only specify the AH. So if you want to get its energy content, you just multiply by its voltage. If voltage 3.7 volt, you just multiply by 3.7. So now then that means 100 AH. If you want to use lower C rate 0.5 C, then that means you can able to run for 2 hours. If 1 C, that means equal to 1 hour at 100 M. If a 2 C, that means 200 M of operation, you can only operate for 0.5 hours. So that's a really simple arithmetic. You can able to get a correlation between the current rating for a battery to the real current you can operate. Certainly, high C rate will be preferred by the charger, but however, that usually degrade the lifetime. So if you always have a supercharge to your battery, then the lifetime is getting lower. So that means we do prefer you, when you have an EV, don't use supercharge that often. Try to use standard charge or medium charge. That will be much more beneficial to the battery lifetime. So here I give you an overall comparison for a number of battery. So you can see that this is a 6 popular type of the battery. The chemical there, they mostly, a number of them consist of cobalt, CO. So cobalt has been one of the popular chemical used in the battery. And then the most famous one is this one, lithium ion. So some people talk about lithium ion, this IRON, that means that kind of iron, not ION. All of them are lithium ion, ION battery, but only this one are using metal ion, right? So we call it lithium iron. So lithium iron phosphate is one of the really popular ones. We like to use them because firstly, it has been heavily manufactured, really mature technology. All the people learn how to do that, so it costs much lower. Today, you can see that you can buy something like 1 kilowatt-hour, this kind of battery, only talking about $1,000. So it's really cheap, really low cost. They're also good battery, have a good lifetime. But the thing is, we try to measure about so-called the specific energy, this one. So I like you to memorize this kind of the parameter. As an engineer, EV engineer, you need to know this. So if anybody asks you what's the energy density, or we use this term, specific energy, mean energy density. WH is the energy content per kilogram to 140. The typical number you need to remember. And then the other good battery is the NMC battery. This few number mean nickel, manganese, and cobalt. So this is also really popular battery. Many of your mobile phone, they use NMC battery because you can see that the energy density, specific energy is highest, really high. So that's why for your phone, because you need really compact. So that's why they use this one. And for some EV, They also like to have really high energy density, lightweight, so that's why they go for this one as well. But however, for the statistic, they see that this one have higher dense and accident as compared to lithium unsulfate. So that's why it's your choice. And some manufacturers, they prefer to use this one because of the safety. You can also see the voltage, different, this one 3.2 volt, 3.2 volt. You see most of phone are 3.7, 3.8. Obviously, they're using NMC battery. If your phone using 3.2, then it's lithium iron phosphate. But seldomly your phone use lithium iron sulfate. Because this one actually have a low voltage, not that convenient anyway. So lithium iron phosphate is one of the popular ones that's been used. I also highly recommend you. Even though in the future, when we use the electric rickshaw boat, we tend to use this one as well because safety. Many of the marine department or manufacturer or approval body do not allow you to use NMC battery for the electric rickshaw, electric boat, because too dangerous. In case anything happen, the people on the boat cannot get away. Not everybody understand how to swim. So the risk restriction in boat are more highly and more strict than the ground vehicle. And another thing I like to tell you, LTO battery is really good. LTO battery is titanium oxide. This battery, although you got lower energy density, but however, the number of cycles is really high, usually up to 10,000 cycles, really good. So probably using this one will be longer than the lifetime for your vehicle. But the disadvantage will be voltage too low, 2.2. Probably you need to connect more battery. You know, the user don't like to connect too many battery cells. If you compare this 2.2 as compared to 3.8, really you need to have double the battery cell. So that means you need to have more wiring connection, then the reliability also more consideration. More wiring, more connection, that means the reliability also in heavy also. Yeah, oh yeah. This one really heavy. You can see that that's the per kilogram. So that means really double. So if you do this one safe, really safe, however, the weight will be double. Which you don't highlight. You can't use them for SUV, right? But probably you can use them for lorry, because sometimes lorry you may able to travel for long distance. You also like to have a really quick charge, because this one able to have a high C rate, 3 times. C rate 10 times the C rate. Most of this battery, LTO battery, they can able to have 10 times C rate. So high C rate means even though high current charging, the batteries won't get really, really hot. That's the key issue. I've been using this LTO battery, even though 5 times C rate, the battery doesn't feel any temperature, doesn't feel any hot. But of course, go to 10 times the C rate, it's really hot, right? But still, you can able to 5 times C rate, then probably you can only about say 10 minutes roughly, you can fully charge the vehicle. I mean, that would be good, really good. So you can see that for commercial vehicle, if you use LTO, that will be really good fit. You see, for private car like what we are doing, we don't really need 10-minute supercharge, because when we park our vehicle in our office, car park, or maybe at home, we can using slow charge. Slow charge is much better for the vehicle lifetime. So that means I think LTO could be something you can use for all the commercial market. And then you can see other vehicle like this two Hobo. This is also really good, but however, the accident rate for Hobo for this battery is the highest among all the battery. Always have accident. So that means the people really scared to use battery with Hobo. Which we don't quite understand why, but we know that this accident rate is really, really high. So it's 3.7 volt, but high accident rate. This one is quite okay, but the energy density is not that promising. This one are using aluminum and cobalt, and this one has been developed for quite some time, but still we think this two is still most popular. So that's how the history of the EV look like. If now you go out to see any vehicle, basically most of them are based on the NMC battery or LFP battery. So these two are most popular. Okay, any question up to this point? So another comparison we like to show to you will be compared with other type of the energy storage. You see other type of energy storage, including first one popular, I want to discuss with you, the red dot flow battery. So we also mentioned to you flow battery. The key reason we use flow battery because it can flow. Flow means the electrolyte inside is the key element to charge the battery. So when the battery being used, then the electrolyte will be depletion. Then we take out and then inject with a new electrolyte. So that means we use liquid form to charge up that battery. And then the used electrolyte will go back to the energy cell to charge up externally in another plant. So that means this technology, we are using the liquid form to charge it. So that's why it's much more convenient. So the voltage of the 1.4 volt is not really high, but it's still quite okay. The C rate is not really high and 0.5 C. But the thing is, C rate may not be too important. If you demand for high current, you can pair them with a supercapacitor. Then in this case, we can able to reduce the current requirement from the battery. That's usually one of the common design we use supercapacitor. You see, we don't want to overload the, say, lithium-ion battery. Although the C rate can be 1 or 2, but if you always operate C rate 2, the battery lifetime can be degraded. So usually we will work together with a supercapacitor in parallel. So in case we demand high current, like we want to overtake another vehicle, then we use supercapacitor current. But normal cruising, then we use lithium-ion battery. So that's how we operate. So we try to do some comparison with the lead battery, supercapacitor, and then lithium-ion and massive is a really basic one. We want to do that comparison, and also lithium-C. Lithium-C is the lithium capacitor. You see, lithium capacitor is actually we combine the supercapacitor and lithium-ion battery chemically internally, combine them internally. So when we manufacture the lithium-C, lithium capacitor, we can tailor make for what kind, how much amount of supercapacitor put in here, maybe 50% in here, 50% in here, we'll combine with that one. Or if you want to have a more AC content, we put more lithium-ion technology. If you want higher power, high current, we put more SC in here. So you can tailor make this one, LIC. So in the market, we just something like this will be available. I think from 14 to 50 is now being widely available. You can see that if for 14, that's the one I can get from many websites, 14 W per kilogram, right? This one. I can always easily get something like 30 or 40. So you can see that this one more look like a lead acid battery, energy quantum battery. But however, the number cycle are much better, right? Usually this kind of the LIC 10,000 cycle, I think, so that means it's much better than lithium-ion battery. Supercapacitor usually have 1 million cycle. So let's say, I think 1,000 cycle is too optimistic, usually about 300. Although some manufacturers mention that they can go up to 1,000, but I don't, only when you operate at 0.2 C continuously within 20% to 80% side, that kind of window, you can able to get better. But usually about, as I mentioned, other lectures only 200 to 300. So that's how it look like. So I also mentioned about the cost, the relative cost. If I use lithium-ion as a base, then let's say 0.7. You see 0.7 nowadays, these two prices are really much close to each other now. So that means some people, they will give up to use lead, even though your vehicle start up battery, they may replace it by lithium. You can get some lithium iron form or start battery 12 volt for replacement because they got higher current. When you start your vehicle, when you press the gas, sounds like more powerful, right? And lithium capacitor really expensive, 6.5, and supercapacitor 10 times, more than 10 times. So that means if you want to use supercapacitor, you can't put that much supercapacitor in your system, too expensive. too heavy. So that's why we are not quite welcome to do that. You can see that even though the weight, so this one, 90 to 280 per kilogram, but this is only 4.6, so that is too heavy. So this means, of course, you can't put too much there. So that's the phenomenon of this kind of the battery system. That gives you overall comparison for all the battery system. So let's say it's really basic. We have been used for more than 200 years. That's quite a good long lithium. Today we're all using lithium-ion battery. That's another long. You can do comparison, but these three are more look like the future energy storage. I have a really good back on this flow battery. Flow battery is something we quite like to develop further. The key reason is, no matter how much effort I put on the lithium, I don't think the energy density can go up by a few times. So that means I don't think the battery can able to charge it within 10 minutes, 5 minutes for the full charge. If you do that, you see our calculation, we need a huge amount of the current and charger. The charger and current too expensive. We can't afford that. If the whole city in California, or I don't know how many vehicles, probably will be something look like maybe 20 million of the vehicle. In this case, all become electric. I think we don't have sufficient power source. So that means if we want to have 1C, 2C of charging, we don't have that much electricity. But however, if we convert them into flow battery, we are only charging the electrode. We can charge the electrode in any location. Because just like the gas, just like the kind of the liquid fuel. In the gas station, you take out the used electrolyte and then inject with the new electrolyte. It only takes you a few minutes. And then the used electrolyte, they will charge up back in the system in their own time. So in this case, that would be more realistic. But at the moment, this kind of technology are based on vanadium. I think you check the website. Vanadium is one of the important metal, and the main manufacturing or mining will be in South Africa. The key component is called V2O5, vanadium oxide. They're the key electrode being used in this kind of the technology. So I'm confident in that in the future, I will try to propose some new project in this area. I think that could be one of the winners. And of course, the other possible thing will be lithium capacitor. The thing is we can tailor-make how much amount of the lithium inside to increase the energy density. Like in here, more look like a less battery with a high current rating and also long lifespan. So that's how we look like that. Short circuit. We also test all the components under the short circuit. You see, lithium battery under short circuit will be a disaster, explosion on fire. So lithium battery, we don't allow them to have any short circuit or high current. Lead-acid battery, you know what happened to lead battery when we short circuit? Have you tried that? Quite interesting. I think you all have some experience when you have lead-acid battery here, star battery, you drop your spanner there, the spanner will jump because short circuit and spark current. And it's quite okay. The lead-acid battery will not get explosion, still quite safe. But lithium will get explosion within a second if you don't turn off. But this one's still okay. And then supercapacitor is good because internal impedance or supercapacitor really low. Even though I myself short circuit supercapacitor, they're still good. It's just getting hot and hot, it won't get explosion. So there's the two major manufacturers for supercapacitor. One is called, and I don't remember the name now, two biggest manufacturer, but their manufacturer plant all also in mainland China, in Shenzhen. And I tried them, and when short circuit them, they only get really hot but low exposure yet. Yeah. So that's something nice to hear that. And these two technology, when they combine together, make this one, so they try to use some of their technology so that they still have the capability under the short circuit, still not get explosion. So I think when we try to use all the battery. What we like to have will be safety. So that means under short circuit still safe will be really, really important. So that's why to compare all of them, I think I haven't put in a safety column here. I think this is unsafe, but all, and then this one I haven't tested them yet, but these two are quite safe, and next battery is relatively safer. So that means the future for the battery will be red dot battery, and the LIC will be something we like to work with. So that means the battery. So again, to summarize what we just say, the best battery we should use will be able to have, to be inexpensive, able to provide long lifetime. I think more than 10 years will be more reasonable because most of vehicle will have to use the vehicle at least 10 years. The battery lifetime only about 6-7 years. That means we need to change the battery twice within its lifetime. That is infeasible, right? And also the lifetime high cost at the moment still hindering the development for electric vehicle. And for the environmental safety, we also think into how we recycle the battery. In the end of lifetime, the battery still can be reused them for the second life. The battery at the end of lifetime probably have 70% of the energy content, so we don't throw them into bin or the landfill. We reuse them in the power plant for the backup power. So that's something we need to look into that. And also you can see that the oil price is really high and stable. I'm not talking about oil price is expensive, sometimes really low, sometimes really high, but we know that over the last few decades, the price are fluctuating too much. Even though our gasoline price sometimes is now become $4.50, but last month only $4. It's very unstable. But however, electricity price will be more stable. Why is that? Because electricity generators are based on nuclear, which is more stable, and based on natural gas, slightly more stable, and based on renewable energy. Renewable energy, once you got the PV panel, is really stable. The price is fixed. So that's why electricity costs will be much more stable than oil. So that means in the future, have our EV are based on electricity only. And of course, the price will be predictable. Your cost of running will be much more confident to do that. But of course, something behind will be how about the recycling, about the carbon footprint. We also like to understand more about the carbon footprint. We do have a lot of research paper looking into carbon footprint to see how when we manufacture an EV, manufacture a battery, how much carbon footprint, how that carbon footprint can be offset in the next few years. When we drive an EV, we know that we can have a saving for the carbon footprint. This kind of saving that is compared to the gasoline car. So, but however, manufacture for the battery will cost you another carbon footprint. So my calculation is that you need to drive your vehicle for at least 2 years in order to offset your carbon footprint. So if you only drive for 1 year, 4 years away, then probably you're wasting your carbon footprint. So that's my rule of thumb. So here I will give you another comparison compared to some popular battery in the history of life, including what we say here, lithium ion, nickel cadmium, nickel metal hydride, and also acid. How we compare that? You see, we understand this one, we understand this one, but this two is a really important element in part of history in the last 30 years. Although we don't use them today, but it's nice to compare them to see what happened to them. So like the specific energy, WH per kilogram, that's the parameter we need to know. So remember, lithium iron phosphate 104.40. You need to remember that. And the NC battery will be 200. Yeah, like here. I need to remember a few things. Yeah. Again, remember this 140 for lithium iron phosphate. As an EV engineer, you need to understand that. I don't need you to remember everything, but this number, you know that NMC battery is a range, but probably you can remember 200. 200 is good number. So at least you need to know this. Number of cycle, roughly I think 1,500. You know that. And the voltage is okay, 3.8 and 3.2. We need to know that. And then another thing I need to use the membrane will be how you compare to conventional battery. For conventional battery, I think this one, lead acid, the really conventional one, 35. You remember that? Membrane that 35? So 35. And then you see lithium, roughly 140, 200, that's number, lithium membrane. These two, you don't need the membrane, but you know that nickel metal hydride and nickel roughly 65 to 50, somewhere in between these two. So you can see that in the old day, we only use this kind of energy density. But once we have the lithium, iron, 3 times better. So that's why everybody switched to lithium. In the old day, 20 years ago, all the power tool, and Decker, this kind of power tool, are all using nickel and nickel metal hydride. I think probably in your garage, you still have some power tools. You may still using this one, but probably gradually they move on to lithium ion. But for some old tool 10 years ago, they may still using the nickel. And W is the power, how much W power you can generate. Then you can see that these two roughly about double to each other. So lithium-ion battery will be 300 watt per kilogram. So that given to you how much current you can come out. So these two, you can see that nickel may still have a really high current output. This battery is still quite capable. And the number of cycle, these two only about 1,000 cycle. Not really promising. 1,000 cycle means under the perfect condition. That means 0.2 C, you can able to have 1,000 cycle, but that's not the case. If you use them like a power tool environment, probably only 100 200 cycle. That means after 1 year, you can see the significant degrading for your battery. The cost. So this what about the cost, and then here will be the other cost comparison. Anyway, so you can now see roughly how they look like. So here will be another table to compare to you how the behavior, advantage and disadvantage against each other. So obviously, lithium-ion battery have high density and disadvantage, still highest cost against all the other type of the battery. And the application, obviously, you can see that for electric vehicle, EV, electric vehicle, renewable energy, and energy bank, all energy stores are based on lithium nowadays. Then nickel has been used power tools, but probably not anymore. The poor thing is the membrane effect. As I mentioned last week, membrane effect is a high issue. So that means we have to fully discharge the battery before we fully charge up. Otherwise, the energy storage will be losing out. But having said that, lead-acid batteries still are dominating the market. Some people, they may ask us why we still keep using the lead-acid since the lithium is so good and the price are so close to each other. Why is that? Why still you can see many of our star battery in all the vehicle are still using lead-acid. Why not all switch to lithium ion? Any comment? Mature, yeah. Mainly about that, yeah. Still 100% all even your vehicle, if you are not driving an EV, your star battery is still lead-acid. Only less than 5% are using lithium. Key thing is mature, low cost. You can get really low cost, really cheap. So your vehicle battery, star battery, roughly say 55 AH. You get really, really low cost, as low as $60. Of course, you can buy $600, but as low as $60, you're still able to get one. But for lithium-ion battery, you can't get it so cheap, probably a few $100, maybe $1,000. So you won't spend that money. And then it's really mature technology, really mature, really safe. No problem. Collision, drop on the ground, really safe. Won't get explosion. But lithium-ion battery may scare about you, may get explosion on fire. So that's why people using less battery, they still feel safe. So that's why all the vehicle if they're gasoline vehicle, most of them still using lead acid. And the market is there. The whole market producing or recycling the lead acid battery is still there. So we can't within a few years to demolish them. So that means still quite a good use. So I think for the next many years, lead acid batteries still being keep using all the gasoline vehicle. But after 2035, when we stop licensing the gasoline vehicle, then the lead acid battery will gradually die away. So probably the lifetime for using lead acid battery cannot last for too long. Probably have another 10 years, maybe 15 years of the lifetime. So if your friend working on the lead acid battery, it's time to switch to the lithium within the next 10 to 15 years. Otherwise, this business will disappear from the planet Earth. Just like 30 years ago, when we used the Kodak, the film. During that time, Kodak, the film manufacturer, is the #1 winner for all the photography. But you see, 20 years ago, everybody switched to electronic. So Kodak disappear, bankrupt disappear from the market. So that means somehow we can see the technology, we need to move on. So we know how much lifetime for this one. Just like this tool, you see, NICTAC battery has been so popular 25 years ago. All the power tool, 100% power tool are using NICTAC, but suddenly disappeared because of ROS requirement and the emerging of the lithium ion. Like this one, I got a very good friend, they're manufacturer for the lithium ion phosphate, but it's just suddenly disappeared from the market. Nobody use it. Manufacturing of this full battery is more expensive than lithium. Although lithium metal itself is expensive, because of the nature of this technology, so the manufacturing cost is much lower than this and that. So that's how the system looks like. I guess in a few more years, probably lithium-ion battery will be cheaper than lead acid. So now then, let's look at some parameter so that you understand the most important parameter, like the state of charge SOC. I think we all know about SOC, state of charge. Let's revisit that. So state of charge is defined as a percentage of remaining. It's called remaining. Remaining capacity is maximum capacity. So that means if full capacity is 100 Ah, then how many Ah left behind with is SOC. So state of charge usually mean the charge means AH. But many people, they may prefer also using the energy. Why is that? Because the battery voltage supposedly will be unchanged, constant, say 3.7 volt. During the range of the fully charged to fully discharged, the voltage won't vary too much. I think probably from 3.6, you rise up to 4.2. So roughly the voltage are quite unchanged. So the voltage multiplied by H becomes the energy. But more specifically, because the vehicle itself are using energy, not the AH. So the state of charge is better to define as the energy and state of energy, SOE. Some people, they like to use SOE, but SOC has been really popular because they assume the voltage should be unchanged. So, but estimate of SOC is quite a challenge. Everybody like to understand, to measure properly. But we do a lot of the scenario, we cannot measure SOC properly. Why is the SOC are highly dependent on current? When your vehicle draw high current, the SOC will get lower because the power loss inside the battery. When the current getting less, SOC may go up slightly because less current, less resistance, and then the energy come out can be much better. And SOC we like to measure as not the energy input. You see, when you charge up the vehicle, then the energy stored inside the battery is have one SOC, but more importantly would be how much SOC, how much charge can be delivered from the battery. Is the output SOC will be more important. Input and output are quite different. Some energy when you input disappear as a power loss. It's not that much energy coming out. So for EV part, we know how much SOC we've been charged into the vehicle, but more importantly, how much SOC can come out, right? So that's why we prefer to model the battery to see how much energy can be delivered by the battery. So accurate measurement of SOC is really challenging. Why is that? Because it depends on a number of items, including the battery is really complicated chemical reaction. It's not a simple resistor. So that means chemical reaction, you cannot make sure that all the reaction will be linearly. So that means for different current, different temperature, then of course the chemical reaction will be different. So the energy come out will be different. And then the condition, these are not the internal, external condition affecting SOC. So including how much current, how much pulse current we try to connect to the battery. And also the battery inside the whole battery system are connected by many of the series and parallel of the battery cell. So that means you can see that 800 volt EV, 3.7 volt for each. You got more than 200 of them connect in series. So you can't for sure all of them are equally behave. If they are unbalanced, the voltage and current unbalanced, then of course the actual SOC is not just simple summation for all the battery cell. So each of battery cell have the SOC, but when you have 200 of them connected in series, the total SOC is not a simple summation because this and that one may not match really well. The current may not able to pass through equally all the time. So the actual SOC can be decreased slightly, different from what you original thought. So the characteristics for the battery cell are not equal. Although for a new battery system, initially all the battery could be look like identical. But after a few months or maybe a few weeks of operation, then the characteristic, like the IV characteristic, impedance characteristic, frequency characteristic will be different. So that means SOC will therefore become different. And also, because this is the aging temperature, you see our EV is so big here. Then the temperature of each battery are not equal, even though within a package. A package, some cylindrical cell on here, some on here. Maybe this side will be more close to the motor, getting hotter. This side away from the motor, getting cooler. So the temperature for each of the battery cell are different. If different temperature, of course, the impedance will be different. So that's why the condition, the temperature are quite different. So that means for estimation of SOC, only a kind of the research paper try to say my estimation is more accurate than your estimation. But I don't think you can get a good estimation. In fact, we don't need that good estimation because we know that when the vehicle under different conditions, different power rating, if you want to speed up the vehicle, you're driving at 100 km per hour compared to 20 km per hour, the temperature of the battery are different. Then in this case, the behavior must be different. So the SOC for high speed and low speed must be quite different. So that means SOC estimation is useless, but only give you a roughly idea how much it is. Even though your vehicle showing that how many percent left behind, but maybe after you drive for a little bit of time, waiting in the traffic light, it suddenly change unexpectedly. So this could happen anyway. So anyway, for the future of the battery, we can see that we are looking into also plug-in EV now become really popular. All the hybrid electric, they also have a plug-in feature. We also see that a new battery like lithium sulfur, lithium oxygen have a really good report for the high energy density. But how soon they can become a real vehicle, we are not quite sure. Of course, I think another battery type will be the solid-state battery. I think I already posted homework to you all. You can submit next week. This homework also asks you to look into the solid-state battery. So this one kind of new battery could be the near future for electric vehicle. So again, we visit about LTO. So LTO titanium battery is also quite promising. Firstly, is the temperature range can minus 30 degrees C. So that's really good. I think for lead, maybe 0 degrees C. For lithium, only minus 10 degrees C. If you go for minus 30, that usually will be good for the whole environment in any corner of the earth. The most of the city, I think the lowest temperature will be -20, maybe at lowest -30 for some city in the North Pole or South Pole. So -30 should be good, quite good enough for most of application. The number cycle with more than 5,000, many of them can be as close to 20,000 cycles. So that would be much better than most of the battery anyway. So the C rate is high, 4C C rate. That would be really good for C rate. For C rate, that means 15 minutes you can finish charging. If you discount for top 80% and bottom 20%, probably 10 minutes you can finish charging. So that's to say, if your vehicle using LTO, 10 minutes you can finish charging. That would be really good for commercial application, for taxi or some delivery vehicle for truck. However, the cost is quite expensive, 3 times at least compared to normal lithium. But the disadvantage will be the voltage too low, about 2.2 volt to 2.4. So that means you need to double the number of battery cells. Some people think it's not that convenient because more number of cells, more connection, more cells you need to procure. And energy density is not very good. I think from my table, I say 80 to 120. But you can see that if you go down 80 Wh per kilogram is not really promising, too low. Only about 3 times compared to lead-acid. It's not really promising. So because the energy density is so much lower than lithium ion, many people don't quite like to use it. The thing is, once the energy density is so low, that means you need to put more battery there. Then the rate will be higher. Then you see if you're using a SUV or something like private car, then probably you double the size of battery, impossible. The vehicle becomes too heavy. You see, say a Tesla vehicle, I don't know how much it weighs, say maybe the vehicle will be 2 tons. Then 1.5 tons will go to the battery. If you change in LTO, maybe safer, but the vehicle becomes 3 tons. Impossible. You won't drive a SUV 3 tons. It's more look like a lorry or a minibus. So that means LTO do have difficulty to use in a vehicle. Probably private car is impossible to use LTO because you don't like such heavy battery there. But however, the application can go really well into electric vehicle, both this kind of the traveling. Because for marine application, the heavier the boat may not be too much a problem. Because most of boat can have a really able to survive for very heavy battery. And the water resistant, only the frontage area is resistant. So that means if you have heavier battery, the frontage area may not change that much. So that means the total requirement due to heavy battery may not be too demanding. But for vehicles, it's quite different. The rate will really govern amount of the energy requirement. So another interesting point we'd like to recap to you will be our red dot battery. So red dot battery is something, a new battery. I'd like to recommend to you all to look into that. Just like your PhD in the future, last year PhD, you may put in the red dot battery. That will be marvelous. I'd like you to work on something new, brand new. If you only work on lithium, everybody work on lithium for the last 30 years. So we need to add on something interesting new. So let's see what the red dot battery. We have been mentioned this for many times, right? Let's show what it is. Basically, we based on 3 popular red dot battery. That's a chemical. So then is zinc and bromide. So then vanadium and iron chromium. But these ones are really popular. I got a few friends working on the vanadium. They want to develop the vanadium battery because they come from South Africa. They have very large mine producing vanadium. So that could be a really nice future. So in this future, I can call my friend to ask him to send me some vanadium for you to try. Anyway, so let's look at what it is. So we have an energy cell here. That's called the battery cell. Inside, they got the electron as so. And then they also have separator as the treatment, but the electrolyte they have inside here, but they use have a 210 as their own electrolyte. So that's so-called the what I mean. You can use the electrolyte to fill up this one So once you fill up in here, then these electrolytes, they all are V2O5, that kind of electrolyte. So after the chemical exchange, the V2O5 will change to another V2O5 plus, and then that will be the energy inside will be used up. So we go to the station, we just renew the liquid, we fill up, remove the liquid, we fill the new V2O5, and then that's it. So the good thing is this item only electron, only the metal electron. And so that means if your vehicle, you want to disable it, you just remove all the electrolyte, then become pure metal without any reaction, really safe. So that means you park your vehicle somewhere, you just drain out all the electron, right? Then it's really safe. Even collision on fire, doesn't matter. And the vehicle becomes really light. If you want to fill up, you just pour in your V2O5 into the energy cell. We have gas tank. Look like this. We have tank next to the vehicle. Put in here, you fill up here, then become your energy source. So you can fill up the liquid here only a few minutes, you can fill up. So 2 minutes, 3 minutes, same as the gasoline vehicle. So that's why this is really nice development. If you check the website for V2O5 or the vanadium or so-called the red dot battery, the red dot battery is reduction and oxidation. That's how the name come from. So spend some time to look in that, and then you'll find something quite interesting. So the behavior of this one is same as other battery, about 1.4 volt. So then you need a number of them to connect in series. So at the moment, I myself have done this one for up to about 10 kilowatt of power. So I think next project I need to do will be say 100 kilowatt for the EV application. Maybe 50 kilowatt or 100 kilowatt more look like an EV application. 10 kilowatt only look like more look like a golf car, right? But this kind of thing, even 10 kilowatt, that cell is not that large, about that kind of size. And then we have a tank here to hold the liquid. So a tank like that, and how much is the tank? Roughly about this kind of size tank, similar to a gasoline. Then we run the vehicle for 500 kilometers. So that's really nice. After 500 kilometers, we exchange the liquid. So that's nice. So you can see the future. This energy cell and the electrolyte are separate components. This is only for energy storage. Energy cell means how much power you can produce in electricity. So today I get 10 kilowatt. Tomorrow I can make 150 kilowatt that will be good enough for all the SUV. And then the vehicle with just two main components. So that's why I can see that this car battery will be much better than all the other conventional lithium-ion battery. Because firstly, we know any hazard. If we want to disable the battery, we just turn off all the electrolyte, remove all the electrolyte for our tank. This becomes nothing. V2O5 electrolyte is just chemical. It's not viscosity. It's not any acid. You put your finger there, no problem. And so this one is just full pure natural. So that's why this battery could be safer and wide temperature operation, high energy content, easy to use, quick fill up. So do spend some time to look into that. Of course, another application we are looking into about the durability. So we want a battery to have a higher durability. So something more look like 10 years with some common law we want a battery to look like, because that will more look like EV lifetime. So in the past, then the hybrid vehicle, like Toyota Prius, have been really popular. I think the battery inside can last for roughly 8 years. You see, quite strange. Why a hybrid vehicle battery can last for 8 years, as good as the lithium? If you're just using the lithium, if you're just using nickel metal hydride battery by itself for EV, probably can only use for maybe 2 years. Because lifetime for nickel metal hydride battery is not very good. But nickel metal hydride battery has been used for hybrid vehicle, like the Toyota Prius, Toyota Prius, the hybrid car, then they use this battery all the time. Because at the day of the manufacturing 30 years ago, this is the most popular battery. So they've been using nickel metal hydride battery during that time. But this battery can be used for at least 8 years in their vehicle without too much degrading. Why is that? If you use your mobile phone, use your power tool probably 1 year. But for the hybrid vehicle, they can able to last for 8 years. Much better than your power tool or in the EV in the old day. Why is that? Any thought? Key reason is all the battery, they will tend to operate in 80%, 20%. So we still have 100% here and 0%. In theory, we can operate all this range. But for EV, all the manufacturer will like you to operate in this range. Even if you buy a Tesla, they will set of that range. So this range, you're able to prolong the battery lifetime up to probably 5,000 cycles. If you use this one, this range probably can go down to about 700 cycles, maybe even less. So now then, for the hybrid vehicle means we always have a gasoline to charge your battery. Your battery always maintain at 60%. 60% hybrid. Why 60%? Because they now allow you to have energy 60% to run your vehicle, allow you to charge in or power regeneration to top up. So this is to top up by power regen. So 60% is quite long. So that means for hybrid vehicle, the battery SOC always at 60% unchanged. So that's the best operating condition for battery. So that's why even though they use nickel metal hydride, so lousy battery, they can still able to work for 8 years because they keep using this percentage. But for EV, if you operate on this, probably a few hundred cycles will end of the life. And probably if you're using this one, 500 cycles, maybe probably not, maybe 4,000 cycles, 3,000 cycles. This what we're about is best operation range. So that means that's why hybrid electric vehicle able to use for long period of time, mainly because they don't change. They don't change the SOC, always keep it at 60 because they got a gasoline generator. All right. So that's to say, nighttime is important. All the EV manufacturers now able to make their lifetime 7 to 8 years. All the manufacturers, they will guarantee to be 7 to 8 years because they ask that, but only for 20 to 80%. If you don't do that, they may not guarantee your battery. And then another topic is the end of lifetime management. At the end of lifetime, your battery, we don't want to fall to the landfill. At the moment, we don't have any technology to recycle your battery. We cannot decompose it to take out the nickel, cobalt, and lithium. We don't have that technology. Take out that technology would be more expensive than manufacturing. So they just fall to the landfill. So now then, that's another technology we look into. So probably all this old battery, we call it second life. So we use the battery for some less demanding application, like backup power. Like your PV in your house, you use that battery, probably low cost. Any people, you get it from the landfill, get the battery back your whole house to use a backup power. In case any power interrupt, then you can use your battery, right? And also some battery bank for power system, renewable energy, because when you put the battery on the ground, the weight is not an issue. You can put as many as you like, right? And also safety, also another key concern for the safety. You see, cobalt is one of the key elements for battery, is really unstable. And the temperature operation 150 degrees C will be something getting really unstable. The battery outside temperature can get up to 60 because you see when a vehicle driving, you get under the sunlight, inside temperature, the global effect can be up to 60, maybe higher than that. But internally, the battery will be more than that. Outside 60, inside can be quite high. So that means for any battery with a cobalt chemical inside, the internal temperature get to 150 degrees C, getting really unstable. The battery can get explosion on fire. So that is the case why the cobalt base of the lithium-ion battery is really unstable, really scary, because they have a lot of accident report on the fire or explosion. So manganese and sulfate, they are slightly better. They can able to get to 250 degrees. So that's why when we use the lithium-ion phosphate battery, they're safer because mainly about the temperature effect, they are much able to survive for high temperature. For the manufacturing of this kind of thing is also high critical. Impurity. If anything, you're manufacturing of battery, you need to in a clean room. So you can see positive electrode here, and then you have the electrolyte, and then separator, electrolyte, and then positive polarity. Between them, we cannot have any impurity, any little bit of dust go in there, then you could be a disaster. Because a little bit that when you pass through the current temperature, then this point can become a hotspot. Hotspot can melt your separator. As I mentioned last week, the separator has many holes for the iron to pass through. If a little bit of dust, you get the heat focus on this area, can expand the hole, can get short circuit, internal short circuit. That will become the on fire or on explosion. So that means how the manufacturing of this is really important. We need to avoid all the impurity in there. That's why we need to increase the temperature stability. We need to make sure the whole surface will be evenly distributed so that we don't have any uneven. Anything uneven will cause hotspot, will damage the separator. The separator, we cannot detect anything. We can detect the current, but separator weaken, the temperature or the current impedance of the battery is still very much similar. So that's the issue for how we look into the safety for the battery. And also availability. So manganese and sulfate can able to handle such a good demand. So they have been heavily demanded by a number of manufacturers. And then another issue will be the lithium. At the moment, the lithium mainly exported from South Africa, Argentina, Chile, and Colombia. So there's a lot of the uncertainty for the supply for lithium. The good thing is we see that every year we can hear some new mine of the lithium. So that's why the price are getting lower and lower. With high demand, more people try to do the mining. But however, this kind of the battery, we can see that the lithium itself will be quite okay, but the related component, like the cobalt, manganese, and nickel, the price is not really stable because we can't just use lithium. We also need to use cobalt, manganese, and also nickel. So all these price do need to have some stable in order to make the whole battery manufacturing become stable. So that means you can see that in the future, we anticipate that we need to develop some new battery because of the high demand for fast charging. So that means lithium sulfur, lithium oxygen with something in many researchers are looking on this area. So we see that the future increase in the energy density may not be too promising. Probably increase by, say, 20%, 50% may be quite possible. But further increase for 100% will get really, really difficult. Although we can have promising results from lithium sulfur and lithium oxide. But as I said, the power rating are really small, only for corn battery development. I didn't see too many research papers for large battery development. So I think for large power battery development for high energy density, still a long way to go. So that means at the moment we can get 140 Wh per kilogram or NMC battery 200, but if we want to go to a 300 and 400, it's really, really difficult. I don't see that in coming 10 years. So we need to have a new development for battery technology, not based on the old thing. That means incremental development to improvement, really, really difficult. We need to have brand new concept for the energy development, probably solid state. In another challenge will be considered in Japan, Korea, they've been focusing on manganese system. And United States have been working on the phosphate system. And then you can see NMC battery, nickel, manganese, cobalt, is one of the good technology for many EV nowadays. So that means you can see that lithium iron phosphate are getting big improvement. Occasionally, I can see that lithium iron phosphate can approach to 200 Wh per kilogram of some manufacturer. You see, as I mentioned, only NMC battery can have 200, but now some improvement for iron phosphate can go up to 200. So that's nice to have. We know that iron phosphate is not depend on cobalt technology. The temperature are more stable, so we have a much better safety. So if the iron phosphate can go up to 200 Wh per kilogram, everybody will like it. So that's how the technology will go to. So that means most of vehicle today, manufacturing vehicle, many manufacturer or user, they prefer to use lithium iron phosphate because of the safety. And many of the standard, including those marine department, also prefer you to use iron phosphate for the electric vessel. So that means for HEV and EV, I think lithium iron phosphate could be one of the winner. And of course, for really compact vehicle, high demand for the weight and the energy density, then we still go for the NMC battery. So here will be some example to show you different kind of the battery. So here will be some kind of the carbon nanotube. So some time ago, when I first be 10 years ago, 20 years ago, when I'm looking on battery system, we'll be experiencing some kind of the carbon nanotube. They use carbon nanotube technology to make the battery, to improve the electrolyte. Also electron. So that's how their battery look like. They have 108, 30, and also NMC battery, this kind of battery. So they are all the power battery. When we do the power battery for EV, then we tend to use this kind of the soft package. If the soft package, we have the electron in here, then you unlock about them stack together, and then you connect the electron in such a way. So that's a very common way we try to stack them. Because when we use this kind of the soft package to put them together would be much easier. But if we use cylindrical one, we do have a form factor. We may not able to pack them properly. But having said that, for cylindrical, because the form factor, then the thermal management will be easier because we got more space for the thermal dissipation. So that means, again, for the charging, we mentioned about we got constant current charging, CC mode. So which when we start to charge the battery, initial stage, we are going to use the CC mode. And then for next nearly finish charging up to 80%, we'll change the constant voltage mode. Because we know that we can't continuously to use CC mode to charge because at the last 20% of the charging, CC mode is too demanding. We need really high power supply to do that. And also not good for the battery. Last 20%, if you use CC mode, the battery will die much earlier than you think. The lifespan will get much shorter. And then, therefore, the next portion of charging, we use constant voltage. That would mean we use much lower current. And then next, when we finish charging, we try to use something called the trickle charge to power up. CV mode, CC mode cannot fully charge the battery, only up to about 90-something%. And last bit of the charging, if you want to go up to 100%, or if you want to keep up to fully charged, we need to use trickle charge. But of course, we don't recommend that because you degrade the battery anyway. But if you really like to have a certain journey, you want 100%, then you need to do that. So that's a typical curve for the charging. Do remember the curve. That's also one of the homework. So let's see that. So initially, so the current, we use constant current to charge that region is called the CC mode. Okay. Let me see a pen to sketch it. Right. So this region, you call CC mode. And then after the current go to certain region, and then you can see it in here, capacity go up to 80, something like more 80%, 85%, depend on the battery. Then we will change into CV mode. So now then you can see that the voltage here is called the CV mode. So voltage in here still equal to this here, unchanged. The voltage will be unchanged. So once the battery voltage, we charge, red color means the battery voltage, charge up to here, and then really much close to the end voltage, 4.36. This battery roughly about 4.3. It's close to 4.3, and then we change to constant voltage. The current become no longer constant. We quickly use constant voltage, just attach a 4.3 volt voltage source to here. And then current will quickly can decrease. And then decrease a certain level, and then we change into, we think that we finish charging. I think the capacity will really go up to 99 to 98%. And then we stop from there, we change to trickle charging, some kind of pulse charging. So last is trickle. Trickle charging. So that's how it look like. But most of the battery charging, we only have that region, and that's it. That will go to 80% charging. This still be there, automatically go to here. If you after charging, you continue charging, or if you ask your charger to charge 100%, what happens? Your charger will be first 80% or 85% the UCC. Then they will switch to CV mode. If they don't unplug, they will use trickle charge to top up or maintain the leakage. You see a battery still have some leakage. If you leave them for too long, maybe charge it after 1 hour, you finish charging, you take back your vehicle after maybe tomorrow or after 1 or 2 days, then the leakage will be there to depreciate your SOC. When you take your vehicle, then you may only have 98 or 97. So this will be top-up charge to make sure when you leave your vehicle in the charger, you still top up your battery. So that's how the basic characteristic. You can see that the voltage are rising quite rapidly initially. So in here, I say capacity say 10%, right? You start from 10%, we quickly charge up. Then you can see the voltage go up really rapidly. And then when near to the end of the 85%, 80%, then your voltage go up slowly and then hopefully reach to about the end point voltage 4.3. And then from then, the voltage become more stable continuously. So that's how the charging curve. You get that? I think you all seen that curve, right? I think you are really professional in the curve. You know, so roughly about the capacity. So you need to know this characteristic. So I mean, for different voltage, different capacity, all behave slightly different. And this will be, you can see that the CC mode here, we use 120 something million to charge the battery for about 10% to 85%. I can see that the C rate for this charging roughly about 0.4 something. Yeah? Just simple arithmetic. 140 minutes for about 75% of charging. So roughly about, you can calculate the C rate for the charging, roughly about say 0.4 something. Okay. Anyway, So there's two different ways for pulse charging or trickle charging. So we use CC in the beginning, and then use constant voltage. So you can see how the current look like. And then for trickle charging, we use two methods for trickle charging. One will be we use really small current, probably say 1% or 0.5% of original current, continuously to charge here. For such a small current, the demand for the charger is not that seriously. Or sometimes we may use pulse charging, so trickle charging some pulse. This pulse can go up to maybe 10 to 50% of the original current. The thing is we can't have too high current because the battery already fully charged. When you inject high current, it's really difficult. You need high power source. So we only have a pulse. We just give a pulse to fill up. The pulse is not that frequent. It can be from every second to every minute. So we don't need to be as often as every second, can be every minute or every a few minutes, depending on the battery characteristic. You have some pulse. Inject the upper round and detect the voltage to see if it's fully charged, and you have second pulse. Make sure the voltage will not drop because they need so-called top up. They don't want the leakage to drain away the battery when you put the battery there for too long.
Can you please?
Huh?
Pulse current.
Sorry?
Can you please repeat this pulse current? Second one, I couldn't.
The pulse current, right? Yeah. The pulse current, this one we have really small current, constant to charge. This one pulse current, say original current, say 100 amp. This current can be from 10 amp, 20 amp, that's pulse. The pulse width of them will be really short, talking about within, say, 1 second, this kind of pulse, very small pulse will continue to top up. So that's called a pulse charging or trickle charging. The thing is, if we use pulse, because we cannot use 50 amp or 40 amp, this high current to inject too much power. We only using a kind of pulse circuitry to inject high current pulse to them. Because we need high current power in order to inject further current to the battery. Because in that time, the battery impedance is really high. If fully charged, the impedance is really high. We need more energy, more high voltage to do that. So this is a little bit of high voltage pulse to inject the current to the battery in order to get this kind of so-called trickle charge. Trickle charge mainly to look after when we fully charged, we still want to top up the battery to 100% or then the leakage. Then we can able to make sure there's leakage, the drain current do not drain away too much. Having said that, that trickle charge can also use in here. You see when a battery being discharged for too much, become die. Then one thing you want to recover the battery is to use trickle charge. Then if you find a battery you cannot charge up by system, probably there will be a lot of crystal this deposit in the electrode. Then to do this one, you have to use trickle charge in here to have a warm up the battery so that you can able to recover the battery. So trickle charge use in the end of the charging, but sometimes you can also use in beginner charging to warm up, to wake up the battery. Some battery have been used for 1 year, probably you need 4 bill. But before we do that, probably I will first use my trickle charge to see if I'm able to recover the battery. So that's one of the way to do that. So there's many techniques there. So probably if you follow me to do PhD, then I'll show you all the detail how to do the battery, including all the battery you see today, all the future battery, lithium sulfur, lithium oxygen, and also the most important would be flow battery and the LIC, lithium capacitor. They're all the future battery, how to model them, how to put them together, how to charge them, what the circuit to charge them, correlation with them. So a lot of the thing, that will be another 10 PhD. Okay, so do look into that. If your friend like to do any PhD in EV, help them. Anyway, so battery safety is something important, but so really common battery safety, I just show you in here. For instance, you can see that anode cathode separator. That's a separator I mentioned many times. You got many small holes in here for the ion to pass through. So that's one of the key things. You need to make sure then the separator will be good. Then you can see that the explosion usually happens when internal explosion we cannot eliminate. That mainly due to separator, we create some problem, create a short circuit. So that includes uncontrolled temperature will cause the explosion. You can see that if separator or electrode, we make them, they got some impurity by mistake. Create hot spot. This hot spot under the normal operation accumulate the heat energy there, then you will create internal short circuit. And also you see the separator will become short circuit. That's the issue. We don't want that to be. So that means temperature control important. We need to measure temperature. If you see any peculiar temperature, then we need to stop. Stop means not only external stop, maybe this battery need to be removed. That is something quite important. So to summarize what we have talked to today, I think we will go through briefly about the lithium-ion battery. I think lithium battery is one of the key technology, but today we still see a lot of the cases for lithium-ion battery, including explosion on fire. And so for the battery management system, we're going to go for next week. We're looking into the firewall, how to implement the firewall, how to implement package, and the monitoring system. And then, of course, today we prefer NMC battery, P element battery, and also lithium iron phosphate battery is the two major market player for lithium ion battery. But we know that still are not the new battery will coming in. That's it for today. Any questions? So we finished the chapter for that. So next week we'll start to look into BMS battery management system. That's another important topic, really important. This only show you really basic concept for battery, but next thing how to use electronic to control that. All right, see you next week then. Bye-bye.